All right, so we are going to start, or we're going to finish up 5.2. Okay, so that one. We talked about normal force and weight. Okay, here we go. So we're going to talk today about Newton's laws as far as applying them to a spring. Okay, so how do Newton's law apply when we have a spring? So a spring exerts a, hey, wait a minute. I need to get my spring. Hang on.
It says right here in the notes, but is that right?
No, last name's. Is here.
I hate it when she's not here. It's that same sub.
Keep ready.
She don't like that stuff.
I feel like you want
She's
to.
okay, but I don't know. Yeah, and I feel like she decides it's really important when she's not here. Someone go open the door. Maybe by hustle.
I pledge allegiance to the flag of the United States of America and to the republic for which it stands, one nation, under God, indivisible, with liberty and justice for all. Congratulations. All teams played Ottawa in the first round of the state playoffs this Friday. All students will have to purchase a ticket for the game to go fans. There will be no free student tickets for this game. Parking will be free if you have a valid Gateway parking pass. Soccer trials for any boys who are not able to attend the previous round will be Tuesday, November 9th at 3:15 to 4:30 on track field up in the field. Senior and order cards are available outside the classroom or on the website. Contact Matthew. Community has early fight senior night tomorrow, Thursday, November 4th at 3 p.m. in the big gym. Seniors from band, cheer, football, soccer, and cross country will be ready. Everybody get a
Thursday at 6. Here. Here.
All right, so
The band's not even coming. We're playing the fight song through the microphone.
okay. All right, so we're going to talk about springs and that springs can exert a force when they are stretched or compressed. Now, I thought my slinkies would work good and y'all be able to kind of play with them, but these slinkies look they've seen better days. A lot better days. Yeah, that ain't gonna work. All right, So on a spring, this is a spring that's not very tight, obviously, and that's why it's slinky. But when I stretch it out, so if I were to let go, what's going to automatically happen? It's going to bounce back together, okay? So that's what we mean by there's a force that gets exerted when it's stretched or when it's compressed, okay? The amount of a spring's stretch or compression will vary
with the force applied. So a spring scale, this is a spring scale, and you can look at the back of it. There's literally a spring in there. So I'll pass it around. So you can see it.
It's like what you weigh a fish with.
Yes. This is what they'll, when you go fishing, you weigh the fish. When you're done, this is the spring scale. So you can see on the back, there's the spring. The spring will be stretched or compressed, and that stretching and compression changes with the force that I apply on it. So if I apply this little 50-gram mass, it'll stretch just a little bit, okay? Because it's not a whole lot going to be added to it. As opposed to applying this 500-gram mass, it's going to stretch a whole lot more, okay? So the amount of stretch or compression depends on the force that's applied. The greater the force, the greater the stretch. So that's one thing you need to make sure that you understand. The greater the force that's applied, the greater the stretch or the compression. And you can see that just by playing with it. Now, please don't break these. If you pull too hard, you're going to break the spring, or you're going to make it so that it's like these slinkies and they don't go back together, okay? You can stretch it too much. That's a mess. All right. So moving on. Hooke's law. So Hooke's law is an equation. It's not an actual natural law, but it is an equation that relates the amount of stretch to the force that's applied. So you can see here's an equilibrium length. So equilibrium just means it's 0 point. So if you pick up this spring scale, the way the spring is right now with nothing on it, we would say that that is equilibrium. And we call that our x equals 0. It's not being displaced. Remember, x is displacement. So it's not being displaced. It's right at the 0 point. But when I apply force to it, that spring will move past its 0 point. Okay? And the distance that it moves past that 0 point depends on the amount of force that I attach. If I apply a little force, it moves a little distance. If I apply a lot of force, it moves a lot of distance. Okay? So that is Hooke's law. The force is proportional to the distance that's applied. Okay, so some things you need to make sure you write down. That when the spring is relaxed, there's no change in length, so x is 0. At equilibrium, or when it's relaxed, then your displacement is 0. When the spring is stretched, x represents the distance from the 0 point, or equilibrium. Okay, so when we stretch the spring, the distance it moves from that x point, or that 0 point, that's x. Okay? Hooke's law, this is what you need to for sure know. Hooke's law states that the force exerted by an ideal spring, and we in physics are going to assume that all springs are ideal, is proportional to the distance of the stretch or compression. That's Hooke's law. The force is proportional to the stretch or the compression. So stretching here, compressing being going back. And they're just going to be the same. It's going to go back to the same distance every time. So it's the same thing. Okay? That's Hooke's law. So make sure you have that written down or mark that in your notes. Okay? All right. So here's the formula for Hooke's law. Make sure you write that down. F is equal to K times X, where K is what we call a spring constant. Okay? It just measures how easily that spring can be pulled. One's in a spring scale, there's a really tight spring. This slinky is a really loose spring. So they're going to have very different spring constants. Okay? It's something that you will be given in a problem, or if you have to figure it out, you'll be given what X and F are, and you'll just rearrange. Okay, so it's not a constant number for everything that you have to memorize. Okay, so K is the spring constant, and it is measured in newtons per meter. So you do need to know your units so that you'll understand whether you're getting the right answer or not. All right, force is always in newtons. Okay, and displacement is always in meters. So that means our K is always going to be newtons per meter. The larger the spring constant, the greater the force that has to be exerted. Or you might think of it as being the tighter the spring, like this one. The tighter the spring, the more force I have to apply to get it to move. So the larger the spring constant, the more force has to be applied, and vice versa. Okay? So also write this down because this is going to help you for problems with not just spring constants, but other things. Objects that have zero acceleration are said to be in equilibrium. If it has zero acceleration, meaning it's not moving or it's not speeding up, let's put it that way. It's not speeding up. So objects with zero acceleration are said to be in equilibrium. Okay? And according to Newton's second law, the net force must be equal to zero if an object is not accelerating. Now notice I did not say not moving. I said not accelerating. If an object is not accelerating, then the net force acting on it has to be zero. Okay? Thus, an object in equilibrium is subject to zero net forces. So my equation kind of got messed up. It should be the sum of the forces is equal to zero. If an object is in equilibrium, then the sum of its forces applied to it has to be zero because it's not accelerating, so its forces have to be zero. An object in equilibrium can be either at rest or moving, here's the key, with a constant velocity. Meaning it's not speeding up, it's not slowing down. It's just going the same speed. Okay? And that's Newton's first law, the law of inertia, that says an object is going to keep going with the speed it has and the direction it has until some other force acts on it. Okay? That's inertia. So whatever object, whatever direction it's moving, it's going to keep going in that direction until some other force acts on it. So this is where our little toy comes in. That is going to keep going at that speed forever until a force acts on it. Now, is it really going to go forever? Why not?
Correct.
Not gravity. What's making it slow down? Because inertia just said it's supposed to keep going. So is inertia wrong?
Air resistance.
A little closer. Not quite air resistance. It's a form of resistance. One we're going to talk about in the next section. Friction. Friction is the force that is applied to that thing that changes its inertia. That changes its force from being zero to being something else. If we didn't have friction, that thing would go on forever and never stop.
So is friction like if you roll a basketball when it stops? Is that what stops it? Like, oh, I ran out of, like, I
Yeah.
ran out of like
Yeah. So that's why it's a whole lot harder to stop a car on ice than it is on a regular road, because you don't have as much friction. Friction is what's if it's just sliding or rolling, friction is going to be what eventually stops it. If we didn't have any friction, then it would, keep on going. But we do, thankfully. That would be really weird if we didn't. All right. So that was Newton's first law, is the law of inertia. Newton's second law is F equals ma. The force applied to the force that causes something to move is equal to its mass times its acceleration. Okay. All right, next slide. Force that opposes motion or the motion of one surface over another, here we go, is friction. So write down that definition of friction. Friction is the force that opposes motion of one surface over another. That is friction. And I think that is where we are going to leave off for today. Yep, that's where we leave off for today. So something that wasn't in the PowerPoint slides, but is talked about in your textbook. So I want to kind of make sure we go back to it and make sure it's not in the PowerPoint slides. No, it's not. Okay. Is this thing of tension. So if you look on page 167, string transmit force from one place to another, that's tension. And tension is just a force, okay? Just like weight is a force, or there's a force due to springs. Tension is another type of force. It's the force exerted by a string or a rope or a wire when that wire is pulled tight, okay? So if you have a rope attached at opposite ends and you pull that rope tight, that force that's exerted is tension. And if you notice in your book, it's exerted in opposite directions. Okay? It's pulling in opposite directions. Let's say you cut that string in the middle. If you cut that string in the middle, and hold it to pull it back, try and pull it back together, then that tension force is exerted right there in the middle, going towards each other, being pulled towards each other. So the only main thing you need to understand about tension, if you look at the two examples, they give you some examples of where tension comes into play. So on 5.9, let's look at that example. See if I can find that example in my Google Drive. There we go. All right. So a person hoists a bucket of water from a well and holds the rope, keeping the bucket at rest, as in case 1. So right here, you have case 1. So we have our bucket is at rest. A short time later, the person ties the rope to the bucket's handle so that the rope holds the bucket in place, as in case 2. Okay, so you see here, the man is pulling on the rope to pull the bucket up. In the next one, he's tied the end he was holding, he's tied it to the bucket, and so the bucket stays in place. Is the tension in the rope in case 2 greater than, less than, or equal to the tension in the rope in case 1? So the tension that's on the rope right here, is that the same as the tension he would have when he pulled on the rope? Okay, that's what the question is asking you. So here's our reasoning and discussion here. In case 1, you're pulling upward on the bucket, and so there's tension in the rope. Since the bucket's at rest, the tension has to equal the weight of the bucket because it's no longer moving. And we've already said if something is at rest, your net force on that object has to be, or is in equilibrium, your net force has to be 0. So whatever the weight of that bucket was, that's the amount of force he has to pull that rope with, okay, because the two have to be equal. In case 2, the two ends of the rope exert an equal upward force on the bucket. So now instead of just him pulling in one direction, okay, to get the bucket up, the force is being applied to both ropes. Okay, not just one side. So to see the image more clearly, they've cut the bucket in half. So if you look on the right-hand side, so before, the tension was all on one side. So you've got tension going up here, weight of the bucket going down here. Okay? But on the other side, where you have two ends of the rope tied to the bucket, then the tension in each end is half of the weight of that bucket. Okay? So tension in rope 1, the tension in the rope is less in case 2 than in case 1. Because you're essentially dividing it in half. All right? So that's going to be a concept type question. There's not necessarily a math problem associated with that, unless it is one where it's making sure that you understand that if something is at rest, you have equal forces. So the tension up has to equal the weight down. They might give you a math problem in that sense. But other than that, it's going to be more of a conceptual type problem. So here's another one where you are going to have some math involved and you've got some angles involved too. So this is where it's going to get a little more complicated. All right, so let's say we have a clothesline where we hang out our clothes, and we put the clothespins, the bag with the clothespins, is we hang it in the middle. So it's supposed to go straight across, right? And they've tied it so that it goes straight across. But if you hang something in the middle, what automatically is going to happen? It's going to pull down, okay? Because the weight of the bag is pulling that down. So we know that if the weight of the bag is pulling down, what also has to be going on? You have to have an equal and opposite force going somewhere to even that out, okay? Well, instead of, it's not really going straight up anymore, it's actually going to be going out to the side. It's going to be applied at an angle on that rope, okay? So that force, that upward force, gets distributed to that rope, all right? So it becomes a resolution of forces, becomes a vector problem at that point, okay? So we have, let's see if I can, this way. So we have the rope is going in the X direction, the weight up, that's the Y direction. We are going to, those are my components. So my force is actually going to be applied as a resultant of those two things, okay, at a particular angle. So the tension in the Y direction, which would be the force up, is going to be equal to the tension, the resultant, times the sine of theta. Because if I'm looking for that angle right there, or this angle here, so here's adjacent equal over hypotenuse. Adjacent, or opposite over hypotenuse is what I'm looking for. Okay, opposite over hypotenuse is sine. Okay, so Ty equals T times the sine of theta. And that has to equal the weight, right? Because the forces going up have to equal the force going down. So the weight in the Y direction is going to equal negative mass times gravity. And then you're just going to add those two things together. Because it's not just pulling on one side, it's pulling on the other, on both sides. So that's why you have two of them right here. All three of those forces added together have to be zero. So the tension going in the Y direction to the left, the tension going in the Y direction to the right, and the weight going down. If we add all three of those, they have to be zero. And then they just rearrange and solve for what's missing, which would be T. Okay, so remember, to solve for T, they're going to factor out the T. That would give them 2 sine theta minus mg equals 0. We were told the mass and gravity, of course, is 9.8, and then we're also given the sine is 3.5. So you're just going to plug in and solve. Okay. All right. So with that said, that is all the examples in that section. So I'm going to let y'all spend the remainder of the time doing your homework problems, and I'll put the answers on the board like I did yesterday, so you can copy down what the answers are and then rework them that way. Does anybody have any questions on last night's homework? I think we worked through those during class, so.
Can you do 28?
28, I can. Let's see. Exit out of that. All right, so number 28. All right. So if we always try to draw what's going on here. So here's our floor. And then we're going to draw a chair sitting on the floor. So there's my chair. And then we have a girl sitting on the chair, which this is going to get really funny since I can't draw. There we go. All right. So what are our forces? So first off, in A, it asks us to find the force of, what was it? Draw a free body diagram for the child and find the normal force exerted by the chair on the child. All right, so the child's sitting on the chair, so she has a force down, and that's the force due to weight. There's also the normal force pushing up. The chair pushing up on the child, okay? So the normal force is going to be equal to the opposite of the force due to weight, okay? And I know the child's mass is 9.3. No, the chair's mass is 9.3 kilograms. And that's 9.8 meters per second squared. And so I just multiply that out and I get negative 91. That should be negative 2. So it should come out to be a positive 91 newtons.
Wait, so where did you get those numbers from? Why did you use those?
Okay.
It's the weight of the girl.
It's the weight of the kid and then acceleration due to gravity. Because we're looking for the normal force of the chair on the child. Okay? So we need the child's mass. She's sitting in the chair. So her mass times gravity, that's her weight.
Okay.
And then the chair is going to push up equally up on her. Otherwise, she would be in the floor, right? So it's going in the opposite direction, but it's going to be the same force.
So why did you put the negative?
Because weight is going to be, the force of weight is going down. So I need that negative sign to indicate that it's going down. And the normal force is going to be the opposite sign because it's going up. Okay. So that was A. Okay, on B, I am looking for the force that the floor exerts on the chair and, of course, the child. So B says draw a free body diagram for the chair and find the normal force exerted by the floor on the chair. So I'm going to do this one in a different color. So the chair and the child together are going to push down with a force due to weight, both weights together. And then the floor is going to be pushing back up perpendicular on the chair and the child. And that's your normal force. And that's what we're looking for. So again, it's going to be normal force is equal to negative the force due to weight, or an opposite sign. If you don't want to put the sign in there till last and just make it negative, that's fine, because that's all you're doing. That negative sign just indicates it is the opposite of what weight is. Okay? All right. So it's going to be the same format, mass times gravity. But this time our mass is the mass of the chair and the child together. So the 9.3 plus the 3.7 times negative 9.8 meters per second squared, since gravity is acting down. So when we multiply all that out, we get negative times a negative is a positive, 100, if we round it, 130 newtons. Okay. So on these, it's extremely helpful for you to draw. That's why they tell you in the problem, draw the free body diagram. So when you draw it out, you see the forces that are being applied, and you see the directions in which they're being applied. So you know then that, okay, normal force is acting up. It has to be positive. So it's got to be the opposite of whatever weight is. Weight's acting down, meaning it's negative. So negative times negative is a positive. Okay? Make sense? Any other ones from last night? Okay. All right, so work on tonight's 21, 22, 26, and 27. No, that's not it. Yeah, 29 and 30. Okay.